Welcome to another deep dive. Today we're going to be tackling something that's kind of invisible, but powers pretty much everything we do online. Computer networks.
Yeah, these things are everywhere, but most people don't even think about them.
Right. You click a link and a web page magically appears,
Yeah.
but there's so much going on behind the scenes, and luckily we've got a stack of documents here that break it all down. We'll be looking at everything from how networks are structured to those essential protocols that make data transfer possible.
TCP, UDP, IP, HTTP, you name it, we've got it.
Exactly. So our mission today is to really give you a solid grasp on how data travels from one computer to another across the globe. And, maybe even uncover a few aha moments along the way.
I think we'll definitely have some of those. The documents we've got here are pretty insightful. They don't just tell us what these protocols do, but they actually reveal the clever design choices and the trade-offs the engineers had to make.
Oh, yeah, for sure. So where should we start?
Well, I think the best place to begin is with the fundamental concept of network layers.
Right, like a multi-tiered cake.
Exactly. Each layer has a specific function, and they all work together.
We've got the 7-layer OSI model, which is kind of like the ultimate blueprint. But we can also think about a simplified 4-layer model. Application Transport Network and Link.
That's a good way to grasp the core ideas without getting too bogged down in the details.
And speaking of grasping the core ideas, our sources use a really clever analogy to explain this whole layering thing. Sending a letter.
Oh, yeah. I love that one.
So at the application layer, that's where you write the letter. Then the transport layer puts it in an envelope. The network layer addresses it, and the link layer physically delivers it to the next stop on its journey.
It's such a great way to visualize how each layer builds on the one below it.
Totally. And what's interesting is that routers, those traffic directors of the internet, they mainly operate on the first 3 layers.
Right. They're like postal workers just focused on getting that letter to the right destination.
But not necessarily reading the letter itself.
Exactly.
Makes sense. So now let's zoom in on the application layer. This is the top layer where we actually interact with the internet through applications like web browsers and email clients.
We're talking protocols like HTTP, which makes browsing possible, and SMTP, the protocol behind email.
Okay, so HTTP is all about fetching those web pages we see every day, right?
Yep, they're built with HTML and often contain various objects like images and videos.
Like a multimedia package.
It's like ordering takeout online. Your browser sends an HTTP request, and the web server delivers the requested meal, which is the web page you see.
I like that analogy. Now, our sources dive into the nuances of HTTP, like the difference between persistent and non-persistent connections.
Ah, yes, that's a good one.
So imagine ordering pizza. With non-persistent HTTP, it's like making separate calls for every topping.
Oh, so inefficient.
Right, but with persistent HTTP, it's like placing one order for everything, much more efficient.
Much smoother.
And then there's web caching.
Ah, yes. That's like your local pizzeria storing copies of popular pizzas. If someone orders one, they get it super quickly because it's already prepped.
And web caching does the same for frequently accessed web pages.
Speeding up loading times and reducing internet traffic.
Smart.
Yeah.
Okay, now what about email? Looks like SMTP is the mail carrier here, taking your message from your email client and delivering it to the recipient's server.
Right, and one key difference between HTTP and SMTP is that HTTP is a pull protocol, meaning your browser pulls information from the server. But SMTP is a push protocol where your email client pushes the message out.
So it's like going to the library to borrow a book versus dropping a letter in a mailbox.
Exactly, 2 very different ways of getting information across.
And it's worth noting that email, unlike web browsing, relies heavily on plain text. Efficient, but a bit old school in today's multimedia world.
Yeah, true that.
Yeah.
But hey, sometimes simple is best.
Right. Okay, so we've got HTTP for web browsing, SMTP for email. But what about those human-readable domain names, like Google.com? How do they get translated into those numerical IP addresses that computers actually understand?
Ah, that's where DNS comes in, the domain name system.
DNS, it's like a giant phone book for the internet.
Exactly. Without it, browsing the web would be a nightmare.
Yeah, can you imagine having to remember a string of numbers for every website?
Not a chance.
All right, so we've covered the application layer where we interact with those familiar internet services. But now let's move down to the transport layer.
The layer responsible for making sure data is transferred reliably between applications.
And this is where TCP and UDP come in, the 2 main transport layer protocols.
Think of TCP as the registered mail of the internet, offering that guaranteed delivery service.
Okay, so reliable and trustworthy.
Exactly. But UDP, on the other hand, is like sending a regular letter.
Yeah,
faster, but with no guarantee of arrival.
So you trade reliability for speed.
Right. It all depends on what you're trying to achieve.
Now, our sources really get into the weeds with TCP, explaining the three-way handshake it uses to establish a connection.
Oh, yeah, that's a classic. It's like two people shaking hands before having a conversation.
Just making sure they're both ready to chat.
But wouldn't that create a lot of overhead?
But it seems that once the connection is established, TCP uses sequence numbers, acknowledgments, and timeouts to guarantee that data arrives in the correct order and without any loss.
So it's like meticulously labeling each piece of a message, confirming receipt of every single piece, and resending anything that goes missing.
Exactly. Very thorough. And our sources also explain how TCP manages the flow of data to avoid overwhelming the receiver.
It's like adjusting a faucet so the glass fills up but doesn't overflow.
That's flow control. But there's also congestion control, which focuses on preventing gridlock on the entire network, not just between two specific devices.
Right, so it's like traffic management on a highway, trying to keep things moving smoothly, even during rush hour.
Makes sense. So we've got TCP, ensuring that reliable data delivery. But what about situations where speed is more important than absolute reliability, like live streaming or online gaming?
Ah, that's where UDP shines.
Right, because it's leaner and faster since it skips all those reliability checks.
It's like watching a live sports event. You might miss a pixel or two here and there, but it's better than constant buffering interrupting the action.
For sure. So TCP for reliability, UDP for speed. Now let's dive into the network layer, the realm of the internet's most famous protocol.
IP, the Internet Protocol.
The one everyone's heard of.
It's like the postal code system of the Internet, responsible for addressing and routing those data packets across networks.
And our sources primarily focus on IPv4, the most widely used version.
Right. They explain the structure of its datagram and those key fields like source and destination IP addresses.
It's like a passport for each data packet containing all the necessary information for its journey across the internet.
And one field in the header TTL, or time to live, is particularly clever. It prevents packets from getting stuck in routing loops and endlessly circulating on the network.
It's like a self-destruct mechanism, ensuring that data packets don't become lost at sea on the internet.
Precisely. And the documents also touch on fragmentation, which breaks down large data packets into smaller pieces that can travel over networks with different size limits. Think of it like trying to fit a large piece of furniture through a narrow doorway. You have to take it apart and reassemble it on the other side.
Makes sense. And speaking of fitting things in our sources, explain subnetting, a technique that lets us divide networks into smaller subnetworks, just like neighborhoods within a city.
It's all about efficiency and organization.
Right, subnetting helps with IP address management and even improves security by isolating different parts of the network.
And then there's CIDR classes interdomain routing, which offers even more flexibility in managing IP addresses.
Like using a more precise measuring tool to minimize waste.
Exactly. So we've got ways to efficiently allocate IP addresses. But how do devices actually get these addresses?
That's where DHCP comes in, right?
Yes, DHCP is like a hotel receptionist automatically assigning IP addresses to devices as they connect to the network.
So no need to manually configure each device.
Especially in a large network, which would be a nightmare.
It's like a plug-and-play system for the internet.
Okay, but what about devices on a private network, like your home network, that want to access the public internet? That's where NAT comes into play, doesn't it?
Absolutely. NAT allows multiple devices in a private network to share a single public IP address.
So it's like having one phone number for your entire family, with each person having their own extension.
Perfect analogy.
Our sources highlight that NAT offers benefits like conserving those precious public IP addresses and enhancing security by masking the internal structure of your network.
But remember you mentioned earlier that NAT violates the end-to-end principle of the internet.
Oh, right. Are there any alternative approaches being considered? Or are we stuck with this compromise? That's a great question and one that deserves further exploration. But first, let's take a look at the link layer. Is the layer responsible for actually transmitting data over those physical mediums like wires and cables?
Think of it like the postal carrier who takes your letter from the post office to its final destination.
Right, and our sources explain that the link layer does more than just delivery. It also handles things like framing, which is encapsulating data packets into neat little packages called frames.
Okay, so organizing the data for transmission.
And it also does error detection, making sure those packages arrive intact.
Like making sure the letter doesn't get ripped or damaged in transit.
Exactly. And in the case of broadcast links, where multiple devices share the same transmission medium, the link layer has to play traffic cop, preventing collisions between those data packages.
So it's like a busy intersection with everyone trying to cross at once. You need some rules to prevent chaos.
Exactly. And that's where multiple access protocols come in, like Aloha slotted Aloha, CSMAC-D, and CSMAC-E.
Wow, so many acronyms. But essentially, they're all about coordinating transmissions and avoiding those digital fender benders.
Think of it like having a set of traffic signals to ensure smooth flow.
Okay, so we've got traffic lights for data.
Pretty much. Now, our sources also delve into Ethernet, the dominant technology for wired networks. They describe Ethernet frames those data packages, zipping across cables, and highlight key elements like MC addresses, which are like unique serial numbers for network devices.
And then there are switches, those intelligent traffic directors of wired networks. They learn MC addresses and use this knowledge to efficiently forward frames to the correct destination.
It's like having a super efficient mailroom where every letter gets delivered to the right person instantly.
I like that. And to minimize those digital traffic jams, switches help segment networks into smaller collision domains, like creating dedicated lanes on a highway.
Precisely. And to further enhance network organization and security, routers are used to segment networks into broadcast domains.
Hmm. I'm trying to picture that.
It's like creating soundproof walls between rooms, preventing noise from traveling from one room to another.
Okay, got it. So we've
Yeah.
covered layers, protocols, and the hardware that makes it all work. But how does data actually find its way through this complex web of networks? That's where routing comes in, right?
Exactly. Routing is like planning a road trip, figuring out the best route to your destination.
Considering distance traffic and road conditions.
Exactly. And our sources explain that routing involves two main functions. Forwarding, which is like a local decision about which road to take at an intersection, and routing, which is the bigger picture of mapping out the entire journey.
So forwarding is tactical, routing is strategic.
Right. And to do this, routers rely on routing tables. They contain information about network destinations and the best paths to reach them.
Like a map.
And these tables are built and maintained using routing protocols like RIP, OSPF, and BGP. They're like the scouts of the internet, constantly exploring new paths and updating the maps.
So it's like having a dynamic GPS system that's always adapting to changing road conditions.
Exactly. And as the internet continues to grow, we're seeing new technologies and approaches to routing emerge, like software-defined networking or SDN, which promises greater flexibility and control over how networks are managed.
SDN, it's like having a central traffic control center that can monitor and adjust traffic flow across the entire network in real time.
Precisely. It's a fascinating area of innovation in networking.
It really is.
Yeah.
And we can't forget about the advancements in network infrastructure itself, with the rise of fiber optic cables and 5G wireless technology.
We're seeing incredible leaps in speed, capacity, and reliability.
It's amazing to think about how far we've come from the early days of the internet.
And I'm sure there are even more exciting developments on the horizon.
Definitely. But for now, I think we've covered a lot of ground in this first part of our deep dive. We've explored the fundamental concepts of computer networks, from layers and protocols to hardware and routing.
We've seen how data is packaged, addressed, transported, and delivered across those invisible highways that power our digital lives.
And we've even touched on some of the challenges and opportunities that lie ahead.
So stay tuned for the next part of our deep dive, where we'll delve deeper into the intricacies of TCP and IP, those workhorses of the internet.
We'll unpack the details of their structure, functionality, and how they work together to ensure reliable data transfer.
So if you're ready to level up your networking knowledge, join us for the next part of our journey.
Until then, happy surfing.
Yeah, it really is mind-boggling when you think about it. All these intricate components working together to create what we just see as, a seamless internet experience.
Right, we click a link and boom, there's the website. But like you said, behind the scenes, it's a whole symphony of protocols and technologies.
Speaking of symphonies, you mentioned TCP's three-way handshake earlier. It's like this elaborate greeting ritual before any data exchange can even happen.
Our sources break it down as a series of messages. First, a SYN packet, kind of like saying, hey, want to chat?
Right. And then a SYNACK comes back like, sure, let's talk.
And finally, an ACK to seal the deal.
It does seem a bit much for just starting a conversation, though, doesn't it?
Well, establishing a reliable connection is super important for TCP. It's like making sure you have a clear phone line before starting an important business call.
You don't want any dropped words or misunderstandings.
Exactly. And once that connection is established, TCP goes to great lengths to ensure reliable data transfer. I'm really intrigued by these sequence numbers and acknowledgments.
Yeah, the sources explain that TCP basically numbers each segment of data, kind of like chapters in a book.
So the receiver can put them in the right order.
Exactly. And then the receiver sends back acknowledgments for each segment, confirming receipt.
So it's like signing for a certified letter. You're confirming you received each piece.
But what happens if a segment gets lost along the way?
Well, that's where timeouts come in. If an acknowledgement isn't received within a certain time frame, TCP just assumes the segment is lost and retransmits it.
Like sending a carrier pigeon with a message, and if it doesn't return, you assume it got lost and send another one.
Exactly. So TCP is constantly monitoring the flow of data, checking for missing pieces, and resending anything that goes astray.
But wouldn't all this back and forth create a lot of overhead? How does TCP balance reliability with efficiency?
Well, it seems TCP has a couple of clever mechanisms for that. One is flow control, which is like a pressure valve. It prevents the sender from overwhelming the receiver with data.
Oh, like a conversation where one person talks nonstop and the other can't get a word in. Flow control makes sure both sides can speak and listen at a manageable pace.
Exactly. And then there's congestion control, which steps in when the entire network is experiencing heavy traffic, like traffic management on a highway, implementing speed limits, and rerouting traffic to prevent gridlock.
Right. The sources explain that TCP uses a sliding window mechanism for congestion control. The size of this window determines how much data can be sent before waiting for an acknowledgement.
So if the network is congested, the window shrinks, slowing down transmission. But if things are clear, the window expands, allowing for faster data flow.
It's really impressive how TCP can juggle all these tasks, ensuring reliability, managing flow, and responding to congestion. And it all happens behind the scenes.
Totally. Okay, so we've covered TCP in depth. Now let's shift gears a bit and delve into the IP datagram format. Our sources provide a detailed breakdown of each field in the header, but it can be a bit overwhelming.
Maybe we should just focus on a few key fields to paint a clearer picture.
I think that's a good idea. For example, the TTL or time to life field is particularly interesting. It's like a countdown timer for each packet, preventing them from endlessly bouncing around the network if they can't find their destination,
Yeah, it's a clever safeguard against those routing loops.
ensuring that packets don't become lost in space on the internet.
Exactly. And then there's fragmentation, the process of splitting large packets into smaller pieces to accommodate networks with different size limits.
Like disassembling a large piece of furniture to move it through a narrow doorway.
The sources explain that the IP header contains information that allows these fragments to be identified and reassembled at the destination, like putting a puzzle back together.
Okay, that makes sense. So fragmentation adds some complexity, but it's essential for ensuring that data can travel across networks with diverse technologies and limitations.
Right. Now, how about we talk about subnetting? The sources describe it as dividing a network into smaller subnetworks, like creating neighborhoods within a city.
Okay, I can picture that. But why is this so important?
Well, subnetting lets network administrators organize their networks more efficiently. They can group devices, logically control traffic flow, and even enhance security by isolating different parts of the network.
It's like having a well-planned city with designated zones for residential, commercial, and industrial areas.
Exactly. And CIDR, or classless interdomain routing, comes into play here as well. It's a more flexible way of allocating IP addresses and routing traffic between networks, making the most of that limited IPv4 address space.
The sources compare it to using a more precise measuring tool, reducing waste and improving efficiency.
Exactly. Now, speaking of efficiency, DHCP certainly deserves a mention. It takes all the hassle out of manually configuring IP addresses for each device on a network.
Right, it's like having a concierge service that automatically assigns you a room key when you check into a hotel.
The sources describe this four-step DHCP process, where a device basically shouts, "I need an address," and the DHCP server responds with an offer.
And then the device accepts the offer and the server confirms, finalizing the IP address assignment.
It's a simple but elegant solution that has made connecting to networks a breeze.
Totally. Okay, but what about devices on private networks that want to access the internet? They typically use private IP addresses that aren't routable on the public internet.
That's where NAT comes in, network address translation,
NAT, it's like a bridge between private and public networks.
allowing multiple devices on a private network to share a single public IP address.
The sources describe NAT as a translator, modifying the source and destination IP addresses and port numbers of packets as they pass through a NAT-enabled router.
It's like having a receptionist who takes your internal calls and forwards them to the outside world using the company's main phone number.
Exactly. And this approach offers several benefits. conserving public IP addresses, which are a finite resource, and enhancing security by hiding the internal structure of the private network.
But you raised an important point earlier. NAT violates the Internet's end-to-end principle, which emphasizes direct communication between hosts. What are the implications of this violation?
Well, it's a question that has sparked a lot of debate. While NAT offers practical benefits, some argue that it introduces complexities, potential performance bottlenecks, and compatibility issues with certain applications.
So it's a trade-off, and the decision to use NAT often depends on the specific needs and priorities of a network.
Right. Okay, so we've talked a lot about IPv4, but our sources also mention IPv6, its successor.
It's like upgrading from a small-town phone book to a global directory with virtually unlimited entries,
IPv6 addresses are 128 bits long compared to 32 bits for IPv4.
providing an astronomically larger address space.
But besides the address space, what are some other advantages of IPv6?
Well, IPv6 simplifies the header, streamlining certain fields and removing others, potentially making routing more efficient. It also has built-in support for IPsec, a suite of security protocols that provide encryption and authentication.
So it's not just about more addresses, it's about a more efficient and secure internet protocol.
Exactly. And while the transition to IPv6 has been gradual, it's gaining momentum as more devices come online and the limitations of IPv4 become more apparent.
Okay, so looking ahead to the future of the internet, now let's move down to the link layer, the layer responsible for actually transmitting data over that physical medium, whether it's copper wires, fiber optic cables, or radio waves.
Think of it as the various transportation methods for delivering packages: trucks, trains, airplanes, even bicycles.
Our sources explain that the link layer performs several crucial tasks, including framing, which is encapsulating network layer packets into link layer frames.
It's like putting a letter into an envelope, adding the necessary address and postage information.
The link layer also handles error detection, using techniques like checksums to verify data integrity.
Like inspecting a package for damage before delivering it, ensuring the contents arrive intact.
And in the case of broadcast links, where multiple devices share the same transmission medium, the link layer has to play traffic cop, preventing collisions between those data frames.
Imagine a busy intersection with cars coming from all directions. You need traffic signals or roundabouts to prevent accidents. That's essentially what multiple access protocols do for data transmission.
Our sources discuss a variety of these protocols like ALOA slotted ALOA CSMAC-E and CSMAC-A.
They each have their own unique ways of coordinating transmissions and avoiding those digital fender benders.
So many different approaches.
ALOA and slotted OLA are like sending messages in bottles and hoping they don't collide.
Okay, I can picture that.
CSMAC used in Ethernet is like listening before speaking and waiting a random amount of time if you hear someone else talking.
And CSMAC-A, often used in Wi-Fi, is similar. But it adds some extra precautions to deal with the challenges of wireless communication.
Right, like the hidden terminal
The
problem.
hidden terminal problem, what's that?
It arises when devices are too far apart to hear each other's transmissions, potentially leading to collisions because they both think the channel is clear.
Oh, so it's like trying to have a conversation in a crowded room where you can only hear the people right next to you.
Exactly. CSMAC uses techniques like RTS-CTS, where devices send request to send and clear to send messages to reserve the channel before transmitting, kind of like raising your hand in class before speaking.
Okay, that makes sense. Now let's talk about Ethernet, the workhorse of wired networks. Our sources describe the structure of Ethernet frames those data packages, zipping across cables, highlighting elements like M-key addresses and CRC for error checking.
MSE addresses are unique identifiers for each network interface card, like a device's fingerprint. And CRC, or cyclic redundancy check, is like a tamper-proof seal, ensuring data integrity during transmission.
So each frame is carefully packaged and protected.
Exactly. And we can't forget about switches, those intelligent traffic directors of wired networks. They learn MC addresses and use this knowledge to efficiently forward frames to their intended destinations.
It's like having a receptionist who knows exactly where everyone sits in the office and can deliver mail directly to their desks.
Switches also help segment networks into smaller collision domains, reducing the likelihood of those digital collisions.
It's like dividing a large office into smaller cubicles, reducing noise and distractions and allowing people to work more productively.
Exactly. And then there are routers operating at the network layer, using IP addresses to guide data packets across different networks. They're like the GPS navigation systems of the internet, constantly calculating the best routes.
And they maintain those routing tables, which are like maps of the internet showing the best paths to reach different destinations.
Right, and these tables are constantly updated using routing protocols like RAP, OSPF, and BGP, which exchange routing information between routers.
It's like having a network of scouts constantly exploring the internet landscape, reporting back on the best paths and road conditions.
And as the internet continues to grow and evolve, we're seeing new routing paradigms emerge, like software-defined networking or SDN, which offers a more centralized and flexible approach to network management.
SDN, it's like having a central traffic control center that can monitor and adjust traffic flow across the entire network in real time.
It's a fascinating area of innovation in networking.
For sure. And then there are the advancements in network infrastructure itself. With the rise of fiber optic cables and 5G wireless technology, we're seeing incredible leaps in speed capacity and reliability.
These advancements are paving the way for a future where the internet is even more pervasive and powerful, enabling new applications and experiences we can barely imagine today.
It's an exciting time to be involved in the world of technology, that's for sure.
Yeah, it's mind-blowing to think about the sheer scale of the internet now. Billions of devices connected, trillions of packets zipping around the globe.
And all happening every second. And yet it all seems to work pretty seamlessly most of the time.
I know, right? We click a link and boom, there's the web page.
We totally take it for granted. But behind the scenes, it's that symphony of protocols and technologies making it all happen.
So we've covered a lot of ground in this deep dive.
Hmm.
From the foundational TCP/IP suite to the nuances of routing and network management tools.
We've really gone deep on how data is packaged, addressed, transported, and delivered across networks, with that efficiency and reliability we were talking about.
Yeah, but like we touched on earlier, the internet wasn't built overnight.
Or it's evolved over decades.
Shaped by some brilliant minds, innovative technologies, and that constant drive to connect people and information.
Which brings us to our final thought for this deep dive.
Okay, are you ready for this?
Lay it on me.
So the documents we've been looking at, they really highlight how crucial the internet has become to modern life. But its future is definitely not set in stone.
That's true. We've talked about the internet's core principles and those ingenious ways we've made it work, and that ongoing shift towards IPv6. But what about the bigger picture? Where's it all going?
Well, the internet was designed with certain principles in mind, right? Like the end-to-end principle, which aims for decentralized intelligence and minimal intervention from intermediary nodes.
Yeah, keep the network as open and flexible as possible.
Exactly. But as we move forward, the internet is going to face new challenges. Increasing security threats, the rise of the Internet of Things with billions of new devices, and demands for even faster speeds and lower latency.
So are you saying the internet's original design principles might not be enough to handle all that?
It's a possibility. We might need to rethink some of the fundamental ways the internet works to adapt to those changing demands.
So new architectures, new protocols.
Yeah, maybe even challenging some of the assumptions we've always taken for granted.
The future of the internet could look very different from what we know today.
It's something to think about.
Well, that's a great note to end on. It reminds us that even though we've explored a lot, there's always more to learn and understand when it comes to computer networks.
It's a constantly evolving landscape.
Who knows what innovations and breakthroughs are just around the corner?
It's an exciting time to be involved in the world of technology.
Absolutely. Well, thanks for joining us on this deep dive into computer networks.
It's been a pleasure.
Until next time, happy surfing.